Good morning, students. I am Suneetha, Assistant Professor of Chemistry from KGC Hanamkonda. Today, we are going to discuss about resonance or mesomeric effect. This is a subtopic of our topic structural theory and organic chemistry. This is the first lesson of second unit organic chemistry. So, let's discuss about resonance or mesomeric effect and its applications. Resonance or mesomeric effect. It is also called conjugation effect. So, resonance or mesomeric effect is generally involves pi electrons, and in some cases, pi and n electrons are also involved in resonance. Whereas in the case of inductive effect, we have already discussed there only sigma electrons are involved. Whereas here in the resonance or mesomeric effect, pi electrons are involved mainly, and sometimes apart from pi electrons, n electrons are also involved. So, what are n electrons? N electrons are non-bonding electrons. They are also called lone pairs of electrons. So, pi and n electrons, they influence the relative electron density in a molecule. So, these pi and n electrons have the influence over the relative electron density of a molecule. And this is observed in molecules having alternate pi and n electrons. So, the effect of pi and n electrons in a molecule is observed, whereas the molecules which contain alternate pi and n electrons. The alternate arrangement of single and double bonds is called conjugation. Now let's see the example. Here C single bond C, then C double bond C, then single bond, double bond, single bond, like this. That is one single bond followed by double bond, again single bond, followed by double bond, single bond, double bond, like this the chain goes, and this is these are called alternate single and double bonds. This is only called conjugation, and such type of diene is called conjugated diene. Conjugated diene. Now, the permanent displacement of 500 electrons of a double bond to single bond is known as resonance effect or mesomeric effect. So, the permanent displacement of pi bonded electrons of a double bond to single bond towards single bond is known as resonance effect or mesomeric effect. Now let us consider this example. Here this is a pi bond. Double bond is made up of one sigma and one pi bond. These pi bond electrons are shifted towards the single bond. Then what happens is the pi bond present in between this carbon and oxygen, it shifts towards oxygen. Thus the resulting molecule is having the positive charge on this carbon and negative charge on oxygen. Sorry, this is negative charge, minus charge on oxygen. So it goes like this. So CH2 double bond CH single bond CH over here. This pi bond electrons transfer towards this CC single bond. Then we will get a double bond over here, and this carbon suffers with a positive charge, and then the pi bond electrons present in between carbon and oxygen, they are shifted towards oxygen. Thus, this oxygen gets negative charge. Here, negative should be there. So, this is acrylaldehyde, where this mesomeric effect we can observe. This positive charge here, negative charge over here. Now, next example is vinyl chloride. So, vinyl chloride. In this vinyl chloride also, this pi bond electrons, the non-bonding electrons present on chlorine, they are shifted towards the single bond. Then what happens? The pi bond electrons present over here, they are shifted towards carbon. Thus, this chlorine suffers with positive charge and a double bond comes over here. And here what happens? In between this carbon and carbon, double bond is not present. And this carbon is having only two hydrogens, that is two bonds. Here one bond, therefore it suffers with a the bond electron pair is transferred towards this carbon. Because of that reason, this carbon should have negative charge. It should be negative. Okay. Next, carbonyl group. There are two resonating structures. If we consider carbonyl group, there are two resonant structures. See, this is carbonyl group. This carbonyl electrons, that is the pi bond electrons present between carbon and oxygen, they are transferred towards oxygen due to bond polarization. Then this carbon gets positive charge and oxygen gets negative charge. Now let's see the definition of mesomeric effect. Mesomeric effect is defined as permanent effect in which pi electrons are transferred from a multiple bond to an atom or from a multiple bond to an adjacent single covalent bond from an atom with lone pair of electrons to an adjacent single covalent bond. So there are three types of transfer of electrons here we can see. That is in the mesomeric effect, in definition of mesomeric effect, what we can say that this is a permanent effect in which pi electrons are transferred from multiple bond to an atom or from multiple bond to an adjacent single covalent bond or from an atom with lone pairs of electrons to the adjacent single bond. This we have already discussed just now. Now I'll show you here. From a multiple bond to adjacent single bond, from a multiple bond to an atom, and from lone pairs of from an atom having lone pairs of electrons to adjacent single covalent bond. So these three show mesomeric effect here. Multiple bond to adjacent single covalent bond, multiple bond to an atom, or lone pairs of electrons are shifted from an atom to adjacent single bond. So this is known as mesomeric effect. Mesomeric effect. So mesomeric effect is defined as permanent effect in which pi electrons are transferred from a multiple bond to an atom or from multiple bond to adjacent single bonds or from an atom with lone pairs of electrons to adjacent single covalent bond. Okay. Now let us see the characteristics of mesomeric effect. The first one is it is a permanent effect like inductive effect, and mesomeric effect is denoted by the letter M. It is represented by the symbol double-headed arrow, and only pi electrons are involved but not sigma electrons. This is the point we should remember always. As the number of resonance structures increases, the stability of the molecule also increases. These are the few important points regarding mesomeric effect. Next, what are the different types of mesomeric effect? Let us see. Types of mesomeric effect. Mesomeric effect is of two types. One is positive mesomeric effect, and the second one is negative mesomeric effect. Positive mesomeric effect and negative mesomeric effect. So, positive mesomeric effect is denoted by plus M, and the negative mesomeric effect is denoted by minus M. Next, let us discuss about positive mesomeric effect. Positive mesomeric effect is the effect that is caused due to the presence of electron donating groups like NH2, H or SH, etc. on the carbon atom. This is only known as positive mesomeric effect. If we consider this example here, single bond NH2. Here this is the NH2 group where a nitrogen atom has a lone pair of electrons. This is shifted towards the adjacent single bond. This is only known as mesomeric effect. Then what happens? The pi bond electrons here, the double bond is present in between these two carbon atoms. The pi bond electrons are transferred towards the carbon atom. Now let us see the resulting structure. So this NH2 is supposed to be the positive charge as it remains and then compared towards the adjacent single bond, and here this carbon it gets a negative charge. This carbon gets negative charge and nitrogen positive charge. So this is known as positive inductive effect. So positive inductive effect is caused due to presence of electron donating groups like NH2 group, chlorines, OH, SH, etc. On the carbon atom. Now next let us see negative mesomeric effect. Negative mesomeric effect This is the effect that is caused due to the presence of electron withdrawing groups like NO2, cyanide, COOH, etc. on the in the carbon chain are attached to carbon atom. Let me say. So here NO2, C and COOH, these are electron withdrawing group. If these are attached to the that is the in the carbon attached to a carbon atom in the carbon chain, which is having double bond in the adjacent carbon. And then what happens due to electron withdrawing nature of these, the pi bond electrons in between the two carbon atoms that shifted towards the single bond present in between adjacent CC covalent bond. Then what happens? The pi electrons in between this carbon and oxygen, they are shifted towards oxygen because this is the bond polarization of this pi bond electrons towards oxygen, as that oxygen is more electronegative. So due to this type of the group, when it is attached to a carbon atom in the carbon chain, then what happens? It withdraws electrons and it attracts electrons towards itself. Because of that reason, the negative mesomeric effect we can observe here. So this pi bond electron shifted towards adjacent single bond. Here pi bond electrons are shifted towards more electronegative atom like oxygen. This is here one mesomeric effect. This here also mesomeric effect we can see. Because of that reason, what happens? This carbon suffers with positive charge and this oxygen with negative. So here positive and here negative. Okay, now let's see one more example. So mesomeric effect is commonly seen in aromatic compounds. So we can observe mesomeric effect in the aromatic compounds. So here we are discussing about aniline. Aniline. Let's consider aniline. Here nitrogen atom, it has a lone pair of electrons. This lone pair is shifted towards adjacent single bond. Then what happens? The pi bond electrons present in the benzene ring shifted towards the adjacent single bond. So here lone pair present on nitrogen atom shifted to adjacent single bond. This is mesomeric effect. And the pi bond electrons, this is alternate pi bonds, conjugated system. In the conjugated system, if pi bond electrons are transferred towards adjacent single bond, that is also called mesomeric effect. So because of this, what happens here? This nitrogen suffers with a positive charge. Nitrogen suffers with a positive charge, and this carbon gets the negative charge. This carbon gets the negative charge and goes like this. Because of that reason, what happens here? We are shifting the electrons from the more electronegative lone pair of electrons from more electronegative atom to adjacent single bond or single covalent bond or sigma bond. And this is only known as positive inductive effect. Positive inductive effect. And let us see this example. This is nitrobenzene. In nitrobenzene, what happens? Here this oxygen is more electronegative. Because of that reason, what happens? The bond polarization is towards oxygen. So oxygen, it pulls this electron pair, that is the pi bonded electrons, towards itself. Then what happens? The pi bond present in this benzene ring, it is shifted towards this bond, single covalent bond present in between this benzene ring and nitrogen. So this is pi bond electrons, shift of pi bond electrons from conjugated system to adjacent single bond, mesomeric effect, and shift of pi bond electrons towards an atom is also mesomeric effect. So here what is that happening? This nitro group, it is attracting, it is withdrawing electrons from benzene ring. So this is nothing but minus M effect or minus mesomeric effect. So aniline is best example for plus M effect, that is positive mesomeric effect. And nitrobenzene is an example for negative mesomeric effect, that is minus M effect. Different applications of mesomeric effect. Mesomeric effect, it has a number of applications. The first one is known as acidity of phenols. Acidity of carboxylic acids. Acidity of carboxylic acids. Third one is basicity of aniline. Basicity of aniline. Next one is stability of carbocations. And fifth one is stability of carbanions. And sixth one is stability of free radicals. Now let's discuss one by one. So these are all the applications of mesomeric effect. First one, acidity of phenols. Acidity of phenols. How do we explain the acidity of phenols? Let's see. Let us see. So phenol is aromatic alcohol. Unlike alcohols, phenols are acidic in nature. When compared to alcohols, phenols are more acidic in nature. Alcohols, they do not exhibit acidic nature, whereas phenols, they exhibit acidic nature. So what is the reason for acidic nature of phenols? So how do you say that phenols are acidic in nature? Because phenols, they react with bases and form salts known as phenoxides. So generally, any compound is called an acid when it reacts with base to form the salt. So here phenols, they react with bases to form salts, therefore they are known as acids. So what is the salt that is produced? What is the name of the salt produced here? That is known as phenoxides. Let me say phenoxides. Now let's consider this example, that is phenol. Phenol, when it reacts with sodium hydroxide, then what happens? The H from this is replaced by sodium metal. Then we get sodium phenoxide, and this H combines with this OH to form H plus and OH minus, gives rise to water. So in this reaction, this is acting as an acid because it is combining with the base to form salt and water. So this is simple neutralization reaction where this phenol, it acts as an acid. Now in phenols, due to resonance, oxygen of OH group gets positive charge, and hence it attracts the electron pair of OH bond, resulting in the release of H plus ions. Why this phenol? It acts as an acid. That we can explain based on the resonance. Then here what happens? The bond between this O and H, here what happens? This oxygen gets negative charge. Oxygen gets positive charge. Oxygen being more electronegative atom, it does not bear positive charge. Because of that reason, what happens? It pulls the electrons between the bonded electrons, single bonded electrons or sigma bond electrons in between oxygen and hydrogen towards it. Because of that reason, this H plus can be easily removed. That is only known as acidic nature of phenol. So this is because of resonance or mesomeric effect. So how do we explain this? Let us see here. Phenols, they exhibit resonance. In phenols, due to resonance, oxygen of OH group gets positive charge, and hence it attracts electron pair of OH bond, resulting in the release of H plus ions. So this is the statement. Now let us see the example. Here, this oxygen, it has a lone pair. So it is shifted towards adjacent single bond. This is only called the resonance. So this is plus M effect. So due to plus M effect of this mm, OH group, then what happens? The bond between this carbon and oxygen becomes a double bond, and this pi bond electrons are shifted towards adjacent carbon. So then here O suffers with positive charge, a double bond is present in between oxygen and carbon, and this carbon suffers with negative charge. This negative charge, if it goes inside due to resonance, because of resonance, then what happens? That is, a pi bond is formed in between these two carbon atoms, and this carbon gets the negative charge. See, pi bond, negative charge. And this goes inside, and here this pi bond comes over here. Then what happens? Here, this carbon gets negative charge, and the double bond in between these two carbon atoms. Finally, it goes inside, and then this double bond shifted to oxygen. Then what happens? We will get phenol. Okay. So this is the resonance. This is the resonance. These are all the resonance structures of phenol, and this is the resonance exhibited by phenol due to the presence of oxygen lone pair of electrons. So when this phenol, it combines with a base, it gives a phenoxide ion and H plus. This is ionization of phenol. Now this phenoxide ion is stabilized by resonance. This phenoxide ion undergoes resonance. How? Let us see. Phenoxide ion with the negative oxygen negative charge, it moves inside. between this carbon and oxygen, the double bond is formed due to shift of electrons. Negative charge is nothing but to a pair of electrons, shift of electrons towards this carbon and oxygen bond. A double bond is formed in between C and O, and this pi bond it shifts towards this carbon, and this carbon gets negative charge. And resonance structures we can give here. This carbon gets a negative charge if it goes inside. Here this carbon gets, if this goes inside, this carbon gets negative charge, and this negative charge if it goes inside. Due to resonance, this oxygen gets minus charge. So these are all the different resonance structures of phenoxide. Due to resonance, and we know that more than number of resonance structures, more the stability. So this phenoxide has number of resonance structures, thus it is more stable. So when compared to phenol, let's see this phenol. In phenol, oxygen is having positive charge and carbon is having negative charge. This is called charge separation. So that a single molecule has two different charges. This is called charge separation. Whenever charge separation is present in a molecule, that molecule is less stable. The molecule is less stable. And with this charge separation, it is less stable. When it becomes phenoxide ion, this in this phenoxide ion, only one single charge is present. Single charge is present on the carbon atom and oxygen, that is negative charge. So this it even this has same number of resonance structures, but the thing is here no charge separation is present. Because of that reason, this phenoxide ion is more stable when compared to phenol. Therefore, phenol tries to be in the form of phenoxide ion, thus it exhibits acidic nature. So like this we can explain the acidic nature of phenol based on the stability of phenoxide ion due to resonance. So since resonance or mesomeric effect is impossible in alcohols, alcohols are not acidic. Phenols are acidic, but alcohols are not acidic, because in phenols we can observe the mesomeric effect, whereas in alcohols such type of mesomeric effect is absent. Thus, phenols are more acidic. Phenols exhibit acidic nature, whereas alcohols do not. Now, second application of mesomeric effect, that is acidity of carboxylic acids. Acidity of carboxylic acids. Now, mesomeric effect can also explain acidity of carboxylic acids. Now, let us consider benzoic acid. Benzoic acid. Benzoic acid is less acidic than formic acid. Then, how do you explain this? The reason for less acidity of benzoic acid than formic acid cannot be explained by inductive effect, but it is explained by mesomeric effect. How? Let us see. See the resonance structures of benzoic acid. Benzoic acid is a COOH group and phenyl, that is phenyl ring or benzene ring. Phenyl group and COOH or benzene ring with C6H5COOH. Now here, this oxygen is more electronegative. It pulls this bond pair of electrons in between carbon and oxygen towards itself. This is the electron withdrawing effect of COOH group. Then what happens? This bond shifts towards this carbon. So this carbon-carbon bond becomes double bond, and this oxygen suffers with a negative charge. Then due to resonance, this goes inside and sorry, what is right, this carbon it has positive charge, and due to resonance this goes there and this carbon gets positive charge. Then due to resonance this goes there and this carbon gets positive charge. See the structures. In this, a positive charge over here, in this positive charge over here, and if it comes inside, this goes there. The first structure we get, these are all the resonance structures of benzoic acid. Acid phenyl group donates electrons towards COOH group, and it causes the and it causes plus M effect. So the N electron density on COOH group increases and H plus ion is slowly released. There is no plus M effect in formic acid. Therefore, benzoic acid is less acidic than formic acid. So in benzoic acid, what is that happening? Phenyl group donates electrons towards this phenyl group. It releases electrons towards the COOH group. It causes plus M effect. So because of plus M effect, what happens? The COOH group, it releases this H plus easily and compared to formic acid. So due to resonance, that is plus M effect of the vinyl group, then what happens? This benzoic acid plus some effect of this. As it is releasing electrons towards this, what happens? This bond becomes strong. When this OH bond becomes strong, this H plus cannot be easily removed. Its acidic nature decreases. Due to plus effect of this benzene ring, benzoic acid is less acidic when compared to formic acid. So this is about the comparison. Acidity of substituted benzoic acid. Acidity of substituted benzoic acid. Now, if it is electron withdrawing groups, the acidity of benzoic acid increases. And in the presence of electron donating groups, the acidity of benzoic acid increases. Now, let's see. Taking an example, let's consider the acidity of nitro, para-nitrobenzoic acid. This is para position, that is para position, nitro group is there. In this para position, OH group is there. Nitro group is electron withdrawing group, OH group is electron releasing group. So whenever electron withdrawing group is present in the benzene ring, the acidity of the benzoic acid increases. Whereas electron releasing group is present in the benzene ring, then the acidity of benzoic acid is increased. So this is what we see. The acidity of benzoic acid increases when electron withdrawing groups are present, like N-water group. This N-water group electron withdrawing group, then what happens? It withdraws electrons from this COOH to benzene to this, towards this oxygen. So that is what happens. This OH from this OH is easily removed. Therefore, it is more acidic. Now, when compared to benzoic acid, it is more acidic due to electron withdrawing group present in the benzene. Now, if you consider this is electron releasing group. When it releases electrons towards this bond and these electrons are released towards this, then what happens? This OH bond becomes more stronger. As this bond becomes more stronger, the acidic, that is, it cannot acidic nature of this para-hydroxybenzoic acid is less when compared to benzoic acid. So this is the order of acidic nature of and here in this molecule minus M effect is present, that is electron with so due to minus M effect it is more acidic, due to plus M effect it is less acidic when compared to this. Okay, next third application of basicity of aniline. So how do we explain the basicity of aniline? Let us see. Aniline forms salts with strong acids. So aniline, it reacts with HCl to form C6H5NH3 plus Cl minus. That is C6H5NH3 plus. This is anilinium ion and this is chloride. So this is, and this plus must be here over nitrogen. So this is anilinium chloride. Anilinium chloride is salt. This is a salt. Now, if this aniline, it combines with acid to form a salt. That indicates aniline is acting as a base. Very simple. This is acid-base reaction. Now, aniline is less basic than ammonia and aliphatic amines. Why? Aniline is less basic than ammonia and aliphatic amines. Now, let us consider aliphatic amine, secondary amine, primary amine, tertiary amine. So, secondary amine is more basic than primary, which is more basic than tertiary, which is more basic than ammonia, and which is more basic than aniline. So, aniline is very much least basic when compared to all these. This is the basicity order. So, here to here, the increasing order. From here to here, increasing order, and this way decreases. Okay. Now, this is due to is basic than all these aliphatic amines and ammonia is because of plus M effect. That is positive mesomeric effect. hybridization, that is resonance of benzene ring. Thus, the basic nature of aniline decreases. Now, let us explain with this example. So, here in H2, nitrogen atom has a lone pair. This is shifted towards this bond. This is only known as what happens. This carbon then negative charge goes inside and this carbon becomes negative. So here charge separation is between nitrogen and carbon atom. There are different charge, minus charge and plus charge. So these are all the resonance structures of aniline. Hence lone pair on nitrogen atom is not available for donation as it has to act as a base in the sense it should accept the proton to donate that lone pair on nitrogen atom to form a coordinate covalent bond. So this lone pair, as it is involved in resonance with the benzene ring, it is not available for donation because of that resonance. Whereas such type of resonance is not possible in the case of aliphatic amines and ammonia. Because of that reason, they are more basic than aniline. So in aniline, due to plus M effect, its basic nature is less. The next application of say mesomeric effect, stability of carbocations. So what is a carbocation? We have already discussed about carbocations in the previous classes. Carbocation is nothing but the species in which carbon bears the positive charge is known as a carbocation or carbonium ion. A carbocation is formed during heterolytic bond fusion. This we have already discussed in the previous classes. Heterolytic bond fusion, homolytic bond fusion. Heterolytic bond fusion produces ions, whereas homolytic bond fusion produces free radicals. Now here, if we consider this molecule CX is more electronegative than C. Because of that reason, if this bond breaks, this X goes with a pair of this bond pair of electrons and it becomes negative, and the CH3 becomes positive. So here, due to heterolytic bond fusion, we got a carbocation. This is carbon bearing positive charges, carbocation. So methyl carbocation is produced here. Carbocations, generally carbocations, how they are produced. The first method is by the addition of acid to unsaturated compounds. When an acid is added to unsaturated compound, generally carbocations are produced. Carbocations are produced. Now let us see this. This one, C double bond. This is the carbonyl group. When H is added, what happens? This one, the polarization of this bond is towards oxygen, as oxygen is more electronegative. Then this oxygen, uh, uh, it captures this proton and it becomes OH, and this carbon is positive charge. This is nothing but carbon positive charge. So this is one method in which, by the addition of acid to unsaturated compound, carbonium ions are produced. Okay. Now another example, this carbonyl carbon treated with AlCl3. Then a bond is formed in between O and AlCl3. Then this carbon suffers with a positive charge, that is a carbonium ion produced. Here C double bond C plus H plus. If we add H plus to one of the carbon atoms here, then other carbon suffers with a positive charge. So here carbonium ion is produced. This is one way where carbonium ions or carbocations are produced. Next, by the addition of acid to compounds containing oxygen. So, when we add an acid to compounds with oxygen. So here let us consider an example. ROH, this is an alcohol. If we add H to this, due to the presence of lone pair of electrons on this oxygen, it donates this lone pair to H plus, forms a coordinate covalent bond. A bond is formed, a covalent bond is formed between this oxygen and hydrogen. And this oxygen suffers with a positive charge due to the bond formation with high H plus. Thus, this OH2 is lost. This is the way in which the alcohol becomes alcohol. Similar way. When this is added to H plus, then what happens is oxygen, with the help of one lone pair, it forms a bond with hydrogen, and oxygen suffers with a positive charge. Thus, it goes R positive and ROH is produced here. Similarly, another example here, alcohol BF3, bond is formed between O and BF3, and oxygen suffers with a positive charge. Thus, it goes along with this bond pair, then R becomes positive. So, like this, carbonium ions are produced. Now, carbocations are classified into three types: tertiary, secondary, and primary carbocations. And how do you say that they are tertiary, primary, and secondary, on what basis? So a carbocation is called primary, secondary, and tertiary when the carbon bearing positive charge is attached to one or two or three alkyl groups respectively. So if we consider this carbocation or carbonium, this carbon having positive charge, therefore it is carbocation. This one alkyl group is attached, then it is known as primary carbocation. So this if primary carbon bears positive charge, primary carbocation. If secondary carbon bears positive charge, is it secondary carbonium ion. If tertiary carbon bears positive charge, it is called tertiary carbonium ion or carbocation. This is methyl carbocation. So the stability order of these carbocations is tertiary is greater than secondary, which is greater than primary, which is greater than methyl carbocation. This we can explain with the help of inductive effect, positive inductive effect of alkyl groups. More the number of alkyl groups, more is the stability of that particular carbocation. So here one alkyl group is attached to carbon, therefore it is primary. Two alkyl groups attached, then it is secondary. Three alkyl groups are attached, then it is a tertiary carbocation. Now next is the another application of mesomeric effect, that is stability of carbanions. So now the anion in which carbon bears negative charge is called carbanion. So they are formed by the heterolysis, that is heterolytic bond fusion. When a group departs from a molecule without the bond pair of electrons, then carbanions are produced. Carbanions may be formed by the following methods. Now let us see the different methods where carbanions, carbon bearing negative charge, they are carbanions. How they are produced? Let's see. This is the one where carbanions are produced when a group or atom departs from carbon atom without its bond pair. Now let us see. This is H. If this H is removed as H plus, then what happens? This bond pair goes towards this carbon. This is having a negative charge, RCH2 minus. This is nothing but carbon with the negative charge, carbanion. Okay. Now here RCOO minus. From this, if CO2 is lost, then R becomes minus. This is the way in which carbanions are produced. Now another one, when a negative ion attacks on multiple bond, then also carbanions are produced. When a negative ion attacks on carbon, multiple bond carbon, then what happens? This X minus, it attacks this carbon. A bond is formed in between carbon and X, and this another carbon suffers with a negative charge. That is nothing but a carbanion. So carbanion is destabilized by the presence of electron repelling groups on it. Carbanion, that is C minus, to intensify its negative charge and destabilize it. So whenever the electron groups are present on carbanion, then what happens? The negative charge on C minus is intensified, that is increased. Thus it destabilizes the carbanion. Now stability order of carbanions. Negative charge, lesser is the stability. So here methyl carbanion more stable when compared to primary carbanion. This is more stable when compared to secondary carbanion. This is more stable when compared to tertiary carbanion. So as the number of methyl groups increases, the electron releasing groups increases, the negative charge on carbon is increased, therefore it is less stable. So here, if we consider methyl, that is ethyl carbanion, this is methyl, this is ethyl carbon, this is isopropyl, and this is tertiary butyl carbanion. So methyl carbanion, there are no alkyl groups attached to this carbon, therefore it is more stable. Whereas here one alkyl group is there destabilizing this, therefore it is less stable when compared to this. And this one secondary, there are two alkyl groups destabilize this carbon bearing negative charge, therefore this ion is less stable. That is methyl groups, where electron releasing groups these are. Because of that reason, the negative charge on this carbon is intensified, increased, therefore thus the order of stability of carbon is methyl is greater than primary, which is greater than secondary, which is greater than tertiary carbanion. Last, the application of mesomeric effect is stability of free radicals. We have already discussed. We know that the free radicals are produced during the homolysis or homolytic bond fission of a covalent bond in the organic molecule. So carbon free radicals are those in which carbon carries one unpaired electron. What is a free radical? We know the species or the atom or group of atoms, that is only called species, which has one electron or odd electron or unpaired electron is called free radical. So if in the organic molecules, if carbon bears one electron or odd electron, then it is known as carbon free radical. Carbon free radical. So these are usually formed by the homolytic cleavage, that is homolysis of bonds at high temperature. Now let us consider this example. This is one molecule in which the homolytic bond fission, the bond between these two carbon atoms is broken homolytically, that is symmetrically. That is, when this bond is broken, one electron of this bond goes with this carbon and another electron of this bond goes with this carbon. Then we get two triphenyl carbon free radicals. Triphenyl carbon free radicals are produced here. Another example here. This is tetraethyl lead. When it is heated to 140 degrees centigrade, then what happens? So we get 4 ethyl free radicals. 4 ethyl free radicals. So this is the way in which homolytic bond fission takes place, and lead free radical will also be produced. And this is the way in which the homolytic bond fission produces carbon free radicals at high temperature. The stability order of carbon free radicals increases with the increase in number of alkyl groups. More the number of alkyl groups, the stability of the free radical also increases. Let us see this example. Here, this is tertiary free radical. This carbon, tertiary carbon, bearing odd electron, bearing an odd electron. This is one methyl group, two methyl groups, three methyl groups attached to this carbon, that is tertiary carbon. Therefore, it is tertiary free radical. Tertiary free radical. Okay. Now, if we consider so this example, let us consider the odd electron present on this carbon is delocalized due to the presence of hydrogen atoms present on these alkyl groups. Here 3 hydrogen atoms are present, here 3, here 3. Now let us consider one methyl group with three sigma bonds, so that we can explain this delocalization readily. Otherwise, this methyl group, these are all same, no difference. So if this bond pair, this odd electron, this odd electron combines with one electron of this bond, then a double bond is formed in between these two carbon atoms. See this, and this hydrogen is having one unpaired electron. So this is nothing but delocalization of odd electron. Due to delocalization of odd electron, similarly we can also show such type of resonance with the help of this CH bond also. Same, this electron and one electron from this double bond is formed, and this becomes a H dot. Here is, and this bond and this electron, one electron from this and this electron, a double bond is formed, and this becomes H dot. This one. So like this, due to the presence of 9 hydrogen atoms, this molecule will be having 9 resonance structures. So more the number of resonance structures, more is the stability. So this is tertiary carbon free radical, which has more number of resonance structures due to delocalization of this unpaired electron present on carbon atom. Thus, it is more stable when compared to secondary free radical. In secondary free radical, it have only 7 hydrogen atoms, whereas in this primary radical, it will be having only 5 hydrogen atoms, whereas this has 9 hydrogen atoms, 9 hydrogen, 3 methyl groups, so each one having 3 hydrogens, 9 hydrogens. If we consider secondary means 2 methyl groups and 1 hydrogen, that is secondary, so 7 hydrogens. If we consider primary in the sense 1 methyl group and 2 hydrogens, that is known as primary. So if we consider tertiary, secondary and primary free radicals, tertiary free radical has 9 hydrogens, so more resonance structures, more stable. Secondary free radical has 7 hydrogens, less number of resonance structures when compared to tertiary, and less stable. Then primary, it has only 5 resonance structures, 5 hydrogens, 5 resonance structures, and it is less stable when compared to secondary free radicals. So all these are more stable when compared to methyl. So tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. Here 9 hydrogens, 7 hydrogens, 5 hydrogens, 3 hydrogens. More the number of hydrogen atoms attached to the adjacent carbon atom bearing the unpaired electron. More is the number of resonance structures, more is the stability. So due to delocalization of odd electron present on carbon atom, the tertiary carbon free radical is more stable when compared to secondary, which is more stable when compared to primary, which is more stable when compared to methyl free radical. So, and generally, carbon free radicals in suitable unsaturated systems are more stable than alkyl radicals due to delocalization of unpaired electron. So, carbon free radicals in the unsaturated systems are more stable than alkyl radicals due to delocalization of unpaired electron. This is the statement we have given. Now, let us consider the example. Here, allyl free radical and triphenyl methyl radicals we have considered. So, this is triphenyl methyl free radical and this is allyl free radical. So, these allyl and triphenyl methyl radicals are more stable than tertiary carbon radicals. So, alkyl radicals, when we compare the stability of these allyl and triphenyl methyl free radicals, alkyl free radicals are less stable, whereas these two are more stable. This is what we said. This is why, because of the delocalization of odd electron or unpaired electron present on the carbon atom. These are more stable when compared to alkyl free radicals. So with this we finish this mesomeric effect. Now let's see what are the different questions we come across from this topic which we have covered. Yes. Okay, thank you. We will stop our topic here and we will continue with the next topic in the next class.